Good morning. So we're going to start today with some of that basic background knowledge for chem. Some of this you guys might remember from physical science, or if you've taken another science recently. I had quite a few people tell me on the survey or the exit questions from last class that we needed some reminders on some of the basics. So that's fine. So if you are ahead of the game and you know this stuff, then this will be a pretty easy week or two. But if not, then these will help you get through the rest of the year. So we're going to get through this. First section, we're going to talk about like what is chemistry. We'll talk branches of chemistry, how that applies to your daily life, and we will end today with a little bit of accuracy and precision and percent error. All right, so I'm going to turn off my camera so you can see the whole page. All right, so what is chemistry? Chemistry basically is just the study of different compounds and how they interact with one another and the things around them. So that can be very, very small. You can be talking on a microscopic level, even smaller than that with atoms. You can be talking about how does the atomic structure of like carbon interact with the things around it. Carbon specifically because it has a very distinct atomic structure, and the way it bonds with things allows it to, or the shape of it, allows it to bond with many different things in many ways. So that's one example of chemistry. So we can talk about things on the molecular level. You can also talk about reaction and energy. So how much heat does something produce? How much light does something produce? And you can use those in things like engineering to get something with the greatest amount of power output. Other ways to look at chemistry is talking about molecules and how they rearrange and recombine to form new things. So that's on a little bit larger scale. Still pretty molecular. You're still talking about something very small, but you're talking about more like things we might do in a lab. So if you're mixing these two chemicals together, why did I get a solid? I mixed two liquids together. How did I get a solid? So that's basically what chemistry is in a nutshell. Other things in chemistry that'll be important just in your daily life are things like names for things. Lots of times, especially, like for one example I have is like my parents. They are 60 or almost 60, and they did not grow up with the internet at their fingertips. And so a lot of times these articles they come across have kind of like the scare tactics. They have those phrases that are scary. They use the scientific words for things. And people write these articles in those ways to grab people's attention, to get their own point across. And it works a lot of the time. You guys, your generation's a lot better about that because you guys, I think, recognize more that you need to vet your sources. You need to go to that website and see, is it a satire site? Is it from an organization that's not reputable? I think you guys do a lot better job of that, even than my students did like 5 or 6 years ago. But an example I have of that is this banana. So if you look over on this side, this is a banana, just a regular banana. And these are all of the, I wouldn't say ingredients, but this is what you would find inside of a banana if you broke it down all the way down to its individual molecules. So if you scan this list, there's a lot of things in there that you probably don't recognize. You probably recognize the sugars probably from biology, but once you get down in here, you have a lot of different acids. There's like thiamine, that's just a vitamin. So you're getting into these bigger words that people don't recognize, but if you learn what they mean and you understand what they are, the whole world just becomes a little bit more relatable. So even just simple things like that. When we're talking about chem and we're just kind of introducing like the branches, you do have your 6 basic branches of chemistry: physical, organic, inorganic, theoretical, biochem, and analytical. So you can kind of see within here some of these different career fields. I know that some of you guys take chemistry because you are going into that career field. So I've had some students come through who are going to be nurses or doctors or something in between or around that. I have a handful of kids every year that want to be pharmacists. There's also a lot of kids in these classes that are going to go into agriculture because chemistry is very important in agriculture. So there's obviously just a lot more to it. Forensics, is another thing. Some people just study chemistry in labs. That's also very important work. So if you're interested in career fields in chemistry, you might want to come back to this slide and just kind of give it a glance and kind of go through those topics a little bit more closely. So even if you are not interested in chemistry as a career necessarily, like let's say you're going to go into business or whatever else, you still come across chemistry a lot in your daily life. So here's just some common examples that you probably interact with on most days. So some of them might not apply to everyone. I'm sure not everyone is using, face creams or bleaching their hair on a daily basis. But if you look through this list, we have cooking and baking. Everything about cooking and baking is chemistry. So this top picture is of onions being sauteed in a pan. You know that when you have an onion, if you were to just bite into a yellow onion, it's really spicy. Usually they're not sweet at all. But when you heat them up to a certain point, it starts breaking down the molecules inside of that and changing them. So when you saute an onion, what happens to it? It turns sweet. It gets to a point where that you've caramelized it is what they normally say. But what you basically have done is change the molecular structure. Bread is another great example. I'm sure you guys know that yeast causes bread to rise. So what's happening, the yeast is actually a living thing, but it's releasing carbon dioxide. The carbon dioxide creates little bubbles that get stuck in the dough. So whenever you're doing that, it gets stuck inside that dough and causes the dough to rise. Other examples would be other things like an engine, any kind of combustible engine. You are using fuel sources and you are pressurizing them to the point of combustion. In some cases, you're igniting the fumes that come off of that, but you're harvesting the energy of different types of substances, and chemistry tells us how much energy you're going to get out of those things. Other examples around your house, you guys may not be super into gardening, but I'm sure you know someone that is. So maybe your parents, grandparents. If you've ever noticed someone with hydrangeas in their yard, these are hydrangeas, okay? So sometimes they're this nice bright pink, red color. Sometimes they're a purple or a blue. The difference in these is not because these flowers are grown to be different colors. It's because of the pH in the soil. So if you create a more acidic or basic soil, you're going to change the color of that flower. Another example of gardening would be things like fertilizers. So if you're in a farming family, I'm sure you're very familiar with different kinds of fertilizers that get sprayed. But just in most people with gardens probably use some kind of plant food or fertilizer. If you look on the back of that, they give out the chemical names or the chemical composition. So when you understand chemistry, you're going to understand a lot of these things in your daily life like a little bit more. You'll have a more clear picture of how things are interacting in the world around you. Other examples would include like mixing ammonia and Clorox. You don't want to do that. So that'll create a gas that is harmful to you. Medications obviously use chemistry. There's a lot of chemistry in creating medications and in the way they interact in your body. Other daily examples might include coloring or bleaching your hair. And my last example on this page is down at the bottom, that little pink picture with all the little bottles on it. Those are face serums. So I'm sure most of you are not worried about that yet. But you might find this in like your mom's medicine cabinet. Face serums with hyaluronic acid are really popular right now. So not knowing what that means might be off-putting to some people, but all it does is it's a substance that pulls water in. So it's like hydrating your skin and makes things appear more plump. Erases fine lines, all that jazz. It's not permanent, but it gets the job done. So these are just some examples of chemistry that you probably come across in most parts of your life on a daily basis. There's a lot more examples. I'm sure that you could think of some, probably things that you've done today. So to start out this unit, we're going to talk about accuracy and precision, and then we'll talk about percent error. So those two things are kind of tied together. So you do need to know the difference between accuracy and precision. Accuracy is talking about how close your values are to an actual measurement. So if you're in a lab and or you're looking at a set of data and you know what the actual value should be, accuracy is how close are your measurements to that value. So if you've calculated it and you know exactly how much product you're supposed to be producing with this reaction, how accurate are you? How close are you to that actual measurement? Precision is a little different. So precision is talking about a grouping of numbers. So let's say you did a lab and you repeated it 3 times to get some data. So you've repeated it 3 times and you've gotten almost exactly the same 3 numbers 3 times in a row. That's precision. So precision is talking more about the measurement versus how close it is to the real value. So if you look at these examples on here, accuracy, this is not the best example of this here, but accuracy is close to the point that you're supposed to be at. This would probably be a better example of accuracy. So this is accurate and precise. So these values are right on target. They're exactly what they should be, and they're all grouped together. So that's the precision. The grouping together is the precision, and the on target is the accuracy. Up here is an example of something that's precise but not accurate. So accuracy would be if all of your numbers were right on target. They're exactly what you calculated. But this is not accurate because all of your numbers are not on target, but it is precise because they are repeated, basically. So you might have gotten a grouping of numbers that are all very similar, but they're not exactly on target. So there's some reasons for that. Usually if your accuracy is off, but your numbers are precise, it usually has something to do with your measuring instrument. So if you're using like an electronic balance to weigh something out and you keep getting the same numbers over and over, but it's not what you are supposed to get, you probably need to look at your measuring instrument. It might not be calibrated. So along with that, you do have a little bit of wiggle room with your error and your measurements. So you are allowed to do just a little bit of estimation. You can estimate the next nearest number, basically. So if you're looking at this picture with the ruler, you have this nail on here. You can see that it goes all the way until 6.3, and then it falls somewhere between 6.3 and 6.4. There are no other markings on this ruler, so you can't with certainty say that it is definitely 6.35, but you can estimate that. So you are allowed to make one estimation past what you can actually measure, as long as you can see that. So we can clearly see that this falls right between those, so you can make the estimation that it is 6.35. Same thing, this happens a lot with our digital scales. So this is what our digital balances look like in class. And when you put something on the scale and it's measuring, if you look at this, it says 10.27 grams. Sometimes this last number here will kind of jump around. It's like the scale doesn't know what it wants to decide on. And sometimes it never settles down and stops moving. So at that point, if let's say this is 10.27 and this last number keeps moving, it's like 6, 7, 8, 9, you can make your best guesstimate of that number. You do not have to reweigh it over and over. You can just say that it's 10.27 and go with that measurement. So that's kind of like your leeway you get with measuring, because we know that measuring instruments aren't perfect. So some more examples of accuracy versus precision. If you had 2 technicians, let's say that we know the accepted value is going to be 2.6 grams per milliliter for the density here. That's what they're measuring. So if we know that the accepted value is 2.6 and technician one repeatedly got almost exactly 2. Okay, so these numbers, they go very far out past the decimal point. So this is a very, very precise measurement, because you get some very exact numbers here. It's also precise because all of these numbers are in a grouping and they're very close to one another. Technician 2, on the other hand, these measurements are a little less precise. There's not as much data given. We don't know if this is 2.90 or if it's 2.93. We're not sure because there's nothing there. But these numbers are very close to 2.6. So even though these numbers are not very close to one another, 2.5 and 2.9 are not very close to each other, but they are pretty close to 2.6. So if you were comparing these two data sets, you would say Technician 1 was very precise, but not very accurate. And data from Technician 2 was pretty accurate, but not very precise. The last thing we're going to talk about is percent error. So percent error is important in chemistry, especially when we start getting into things like stoichiometry and percent yields. So when we start talking about percent yields and things, we'll use this a lot. Percent error is very easy to calculate. So you're talking about the measured value. I'm just going to start back over here with the percent error. Had to start recording before classes and I'm finishing after, so I apologize for that interruption. But percent error is easy to calculate. You're going to take your measured value, so that's the value that you have calculated, or if you're looking at a set of data, it's the data that the technician or the scientist has gathered. So it's your measurement minus the accepted value all over the accepted value times 100. So if I measured 90 and the accepted value was 100, I would have 90 here, 100 here, and 100 on the bottom. You divide that, you're going to get a decimal, so then you need to then multiply it by 100 to turn it back into a percent. Additionally, you'll get positive and negative values. Positive values means that your measurement is higher than the accepted value, and negative means that your measurement was lower than the accepted value. Here's an example of percent error. So your problem's going to say something similar to this. A student measures the density of an object as 1.40 grams per milliliter. The correct or accepted value of the density is 1.36 grams per milliliter. What is the percent error of the student's measurement? We know that the student got 1.40, so this is the the measured value. The actual value or the known value is 1.36. And then we're also going to put that down here. So you'll subtract this and then divide it, multiply it by 100, and you get 2.94%. So since this is a positive value, it means that it was 2.94% higher than the known or accepted value. Here's another example. We're going to work through it together. Sorry about that. Okay. So what is the percent error for a mass measurement of 17.7 grams, given that the correct value is 21.2 grams? So if we know that we have measured, oh goodness, get this figured out. Give me a second. Okay, let me turn this back into a pin. Okay. So what is the percent error? We know that our measured value, or the measured value, is 17.7. We're going to subtract 21.2. And then we're going to put 21.2 on the bottom again, because we know that the 17.7 was what was measured, 21.2 was the given value, and 21.2 is the given value. All of this you will then multiply by 100, turn it into a percentage. So when you're done with that, you're going to end up with something close to 17%. And that was a negative value. So what this is telling you is that your value that you measured, or the student measured, was 17% below the accepted value. So most of the time when you're talking percent error, anything over a certain percentage threshold is going to tell you whether or not to take that as a good measurement. And that will depend on your lab and how much data is taken, as well as how much precision you need in that data. And that's the end for today. So please reach out if you have any questions. The assignment is found on Canvas. There's one assignment over accuracy and precision and some percent error.